All right, welcome to the explainer. From the light switch on your wall to the phone in your hand, there's this invisible force at play, right? Kind of like this hidden magic that makes our whole modern world tick. Today, we're going to pull back the curtain on that force, electromagnetic induction. And we're going to start with a mystery you've probably walked past 100 times and never even thought about.
Yeah, I bet you've seen one of these before. Just a plain, kind of boring, fenced-off building humming away somewhere in your neighborhood. It's a power substation. And they're so common we barely even notice them. But that pretty unremarkable box, it's the final, absolutely crucial link in this incredible journey that electricity takes to get to you.
So, have you ever actually wondered what it's for? Why is it so critical for getting power to your home? Well, inside that box is the solution to a massive, massive problem. A problem that nearly made our electric world completely impossible. And the answer? It lies in a discovery made almost 200 years ago. All right, so let's start with that problem. The whole reason that box even exists. I mean, why can't we just run a wire straight from the power plant right to your house? What's the big deal? Well, the reason is something called ohmic heating. It's a fancy term, but here's what it means. As electricity travels through hundreds of miles of cable, a huge amount of its energy just gets lost as heat. Seriously. If we sent power directly from the plant, most of it would just disappear. It would just warm up the wires and never even make it to your home. It would be a massive, super inefficient waste. So, to figure out how we crack this problem, we have to jump in a time machine. We're going back to the 1820s, to a scientist whose incredible curiosity would change literally everything. And here he is, Michael Faraday. Now, he set up this unbelievably simple apparatus. You've got a coil of wire, right? And it's hooked up to a galvanometer, which is just an old school, really sensitive electricity detector with a little needle. And then he had a simple bar magnet. His question was simple but profound. Could a magnet somehow create electricity? So he takes the magnet, he pushes it towards the coil, and bam! The needle on the galvanometer jumps. Just like that, for the very first time, a moving magnet had created a pulse of electricity out of thin air. But then, something kind of weird happened. When he held the magnet perfectly still right inside the coil, nothing. Zero. The needle went right back down. The magic was just gone. Okay, so he pulls the magnet back out, and the needle jumps again. But this time, it jumps in the opposite direction. The current was actually flowing the other way. And that was the light bulb moment. The crucial thing wasn't the magnet itself. It was the change, the motion. The changing magnetic field was what mattered. So what Faraday stumbled upon is this incredible phenomenon called electromagnetic induction. Now, you see induced EMF on the screen. That's just the sciencey term for the voltage, the electrical pressure that gets created. By simply changing a magnetic field near a wire, Faraday could literally force electricity to flow. This was a monumental discovery. But here's the thing. This new force wasn't just random chaos. Faraday and other scientists soon figured out that it follows very specific and honestly pretty fascinating rules. Okay, so rule number 1 is Faraday's law. To put it simply, it just means that the faster you move the magnet or the stronger that magnet is, the more electricity you're going to generate. More change equals more power. It's beautiful, simple, and elegant. Now for the second rule. And this is where it gets really interesting. Nature literally pushes back. Check this out. When you move the magnet's north pole toward the coil, the current that's created in the coil turns it into an electromagnet with its own north pole. It's actively trying to push your magnet away. And then, when you pull the magnet out, the coil flips its polarity to a south pole, trying to pull it back in. How cool is that? This whole principle is known as Lenz's law. You can think of it as nature's resistance to change. It's basically saying, nope, you can't get free energy. You have to actually do work. You have to push against this opposing force to generate electricity. This is what ensures the conservation of energy in the universe. It's a fundamental rule. So, okay, Faraday showed us that a simple back and forth motion can create a little pulse of electricity. But how do you scale that up? How do you go from that to powering an entire city? Simple. You build a generator. Instead of just moving a magnet in and out of a coil, you take that coil of wire and you rotate it inside a magnetic field. As one side of the coil moves up through the field and the other side moves down, a current is induced. And if you keep that rotation going, you get a continuous flow of current. And remember how when Faraday pulled the magnet out instead of pushing it in, the current reversed? Well, the same thing happens here. This constant rotation means the direction of the current is also constantly flipping, back and forth, back and forth. This creates that smooth, oscillating wave of electricity you see here.
And that wave is what we call alternating current, or AC. And that's it. That's the reason our entire power grid is built on AC, because it's the most natural, direct output of a generator spinning, all thanks to electromagnetic induction.
Okay, so now we've got the power, we're generating tons of AC electricity. But we still have that big problem we started with, right? Losing all that energy in the transmission lines. This is where Faraday's discovery gives us one more incredible, game-changing tool. And that secret weapon is called a transformer. At its heart, it's just two coils of wire wrapped around an iron core, but it's pure genius. It works because the alternating current in that first coil creates a constantly changing magnetic field in the iron core. See where this is going? That changing field then induces a brand new current in the second coil. It's pure induction, but without any moving parts at all. And here's the clever part. A step-up transformer, which has more coils on the output side, increases the voltage. A step-down transformer has fewer coils, so it decreases the voltage. So at the power station, we use a step-up transformer to crank the voltage way, way up. And that box in your neighborhood, you guessed it, that's a step-down transformer, bringing it back down. And this is the genius of the whole system. Remember how we said power loss is caused by high current? Well, by using a step-up transformer to jack up the voltage to hundreds of thousands of volts, we dramatically lower the current for that long-distance journey. This is what minimizes the heat loss, allowing that power to travel hundreds of miles super efficiently. Then, that substation in your neighborhood steps the voltage right back down to a safe level for your home. Problem solved. And this principle, it's not just about the grid. It is absolutely everywhere. It's inside the pickups of an electric guitar, where a vibrating metal string changes the magnetic field to create an audio signal, and it's the key to our wireless future. It's how charging pads induce a current in our phones and electric cars without ever having to plug in a single cable.
So there you have it, from a simple tabletop experiment to a global power grid and the wireless gadgets of tomorrow. Faraday's amazing discovery of an invisible push and pull continues to shape our world in the most profound ways. I mean, after 200 years, this invisible force is still evolving. So what do you think? What's the next great leap gonna be?